Hello students, welcome back. So we were in the middle of a very important discussion of electrochemistry chapter. So today we are just going to focus more on it, and we are going to calculate how to calculate exactly the EMF of the full cell, and how is Gibbs free energy related to EMF of the cell, and how to find out the equilibrium constant using the concept of EMF of cell. Okay, so let's get started. So in the previous lecture we have talked about electrode potential. We have already told that whenever we are dipping a metal rods in its own aqueous solution, so there will be a potential developed which is called as standard electrode potential. Okay, standard word is used when the conditions are standard. Okay, when the concentration of all the species and the partial pressure of all the gases in the solution is 1 molar or 1 atm. Okay, and temperature is maintained as 298 Kelvin and pressure is 1 atm. So whenever there is a tendency to oxidize, so we'll calculate it oxidation potential. If oxidation potential is positive, we'll say that the tendency to oxidize is more. Okay, by default we generally consider electrode potential, standard electrode potential, as reduction electrode potential. Okay, standard reduction electrode potential. Okay, so this was the very basic which we started in the previous lecture, and we also discussed how we are forming a full galvanic cell. Okay, so let me just show you through a small animation to make you understand what we were talking about. Okay, so this was the basic construction of a cell. Okay, so this is an example of a Daniell cell. So in Daniell cell we say that the zinc is dipped in the zinc sulfate solution, that constitutes the anode, and the copper is dipped in the copper sulfate solution, that constitutes the cathode of this full cell. They are connected externally through a conducting wire. Okay, a bulb is attached to indicate the flow of current. Okay, now a salt bridge is also attached to the two solution, which does not allow the mixing of the two solution and neutralizes the excess charge that are produced in the half cells during the course of reaction. So let's understand. Okay, so this was basically your zinc and that is your copper. Okay, so if you can see that we are having zinc rod which is dipped in zinc sulfate solution and a copper rod which is dipped in a copper sulfate solution. That terminal is your cathode, this terminal is your anode. Okay, so if you look closely in this, so we are saying that zinc rod is dipped in a solution containing zinc sulfate ion. Okay, and similarly in the cathodic half we are talking about copper dipped in copper sulfate solution. Okay, so you look at the cathode. Okay, so this is the copper rod which is dipped in the copper sulfate solution. You can see there are some ions in the aqueous solution. Okay, so what happens initially, we know that oxidation takes place and the flow of electron starts taking place. Okay, due to which this bulb will glow. Okay, you can see this. Okay, so the zinc gets oxidized. So you can see at the anode the zinc rod. Okay, some zinc is getting oxidized into zinc 2 plus. Okay, you can see. Okay, the zinc is getting oxidized into the, okay, this is zinc 2 plus, not this is zinc. Okay, so this zinc is getting oxidized as zinc 2 plus. So in solution we know that there is a positive charge going, due to which there would be accumulation of positive charge and there would be excess positive charge. Now the electron that came from anode is entering into the cathode. Okay, the electrons are taken up by the copper 2 plus ion in the aqueous solution, you can see that. Okay, and they are just getting deposited at the copper rod, due to which in solution there will be more negative charge. Okay, so this terminal will have negative charge. Okay, due to which we are connecting the salt bridge. Okay, you see the salt bridge is connected over here. Okay, so this salt bridge will basically pump some of the ions in the solution. Okay, you can see it over here. The salt bridge is pumping some, because this has an excess positive charge, so it is pumping some negative charge, due to which the excess positive charge will neutralize. Okay, and the flow of the current will start again. Okay, hope this is clear to you. And similar thing happens in the cathodic cell as well. Okay, so hope this is clear to you. So we are basically saying that we are having a anodic half. Okay, in the anodic half we had zinc dipped in a zinc sulfate solution. In cathodic half we had copper dipped in a copper sulfate solution. Okay, zinc is getting oxidized, so zinc 2 plus goes in the aqueous solution and the electrons flow from the anode to the cathode through a conducting wire, and the electrons comes in the cathode, that is copper. Okay, now these two electrons or the electron are taken up by the copper 2 plus and they get reduced. Okay, So when they get reduced, we know that this number of sulfate ion in the solution would be more because some of the copper 2 plus has already deposited. So this solution has a negative charge and the anodic solution has the excess positive charge. Now because of these excess charges, further movement of electron won't happen. So we need to neutralize these charges. So that is done through a salt bridge. So salt bridge, we have already told that salt bridge is something like this. Okay, it is a U-shaped inverted tube. Okay, that is dipped in both the solution. This has a porous ends. Okay, which allows the exchange of ions. So the ions that are present inside this can go into the solution, but none of the ions of the solution can enter into it. Okay, so basically we say that it is a U tube containing a solution of a inert electrolyte such as KCl, KNO3, ammonium sulfate or K2SO4. Okay, suspended in a agar or a gelatin. So basically in this salt bridge we are having a gel, and that gel is also having a inert electrolyte like KCl, KNO3, K2SO4 and NH4NO3. Okay, so what it basically does when you just add it, okay, when you just introduce a salt bridge in the solution, okay, you can clearly see that we know that there was an excess positive charge developed. So this salt bridge will pump out some negative ion in this solution so that the positive charge gets neutralized. And similarly this side, the cathodic side, has the excess negative charge. So the salt bridge would pump out some positive cation or the cation so that the solution gets neutralized. So when the solution gets neutralized, again the oxidation will happen. Okay, again the electron will flow. Okay, and whenever there is an excess charge developing, the ions from the salt bridge will keep on migrating towards the respective electrode, respective solution to neutralize them. Okay, so this is how the internal flow of current happens. Okay, so internal flow of current is just due to the movement of ions from salt bridge into the solution. So that is how the entire, okay, solution or the entire circuit is complete. Okay, hope this is clear to you. So the function of the salt bridge is to complete the electrical circuit. So the first point is very important. So it is basically the function of the salt bridge is to complete the electrical circuit. Okay. The second is to maintain the electrical neutrality of both anodic and cathodic chamber without mixing the two components. So salt bridge basically pumps out the ions of the electrolyte and neutralizes both the cathodic and anodic chamber. Okay. Now the third point is very important. This minimizes liquid junction potential. Now I am going to talk about this like in a little later when we are talking about electrochemical series, electrochemical cells with transference or without transference. Okay, so I will just make you understand the basic what is liquid junction potential. Okay, suppose we had the anodic portion. Okay, this was the anode and this was the cathode. Okay, a rod was dipped in it, and we are just connected it with a conducting wire. So there is no salt bridge in this, but we are having a membrane. Okay, so this is basically a semi-permeable membrane type of thing. Okay, so this membrane allows some ion to pass through this. Okay, and through that they can neutralize, okay, the excess positive and negative charge. So we know that in anode oxidation is taking place. So the rod, okay, the metal gets oxidized, it enters into the solution as ion. So there is a development of excess positive charge. Now these electron enters into the cathode. The ions in the electrolyte, the cation in the electrolyte get reduced and the solution has excess negative charge. Okay, so to neutralize this excess positive and negative charge, we will say that the excess positive charge has deposited over here. Okay, similarly excess negative charge would deposit over here. Okay, so to counterbalance them, the number of positive charge which is over here would be equal to the number of negative charge over here. So there would be an electrical double layer that is set up again. Okay, so this would lead to the again a potential, okay, that would decrease the overall potential of the cell. So this is basically called as the liquid junction potential. Okay, so at the junction of the two liquid there is a potential developed which will decrease the overall EMF of the cell. So what we are saying over here is, okay, we will not have this kind of setup, rather we will separate the two solution and we will use a salt bridge so that such kind of liquid potential does not develop. Okay, and the role of the salt bridge is to minimize this liquid junction potential, due to which, okay, the EMF will obtain will be much more. Okay, so this is the concept. So salt bridge is basically used to complete the entire circuit to maintain the electrical neutrality of the cathodic and the anodic chamber without mixing of the two solution. And the third is, if we are not taking the salt bridge, if we are having a membrane, okay, that is separating cathode and anode. So basically in the cathode there would be development of excess positive charge, and in the anode there would be the development of excess positive charge. In the cathode there would be development of excess negative charge, due to which the positive and negative charge at the junction would orient, and it would lead to a formation of a double layer, which would lead to a potential. So that would decrease the overall potential of the cell. So what we do, we separate these two solutions and we join them through a salt bridge. So the role is to minimize the liquid junction potential. Okay, hope this is clear to you. Now one very important point which you should know, in this salt bridge we are taking specific electrolytes like KCl, KNO3, K2SO4 and NH4NO3. We are not taking any general electrolyte. So how do we choose the electrolyte present inside them? So what they have to do, if you are connecting with cathode and anode, so they have to basically pump out the ion to neutralize the excess charges. Now to pump out, both the cation and anion should have similar mobility, okay, because if one solution is having positive and the other solution is having negative, so if the salt bridge pumps out at the same rate, both the ion move in these solutions and neutralize them, then both the solution will be neutralized at one particular point, okay, and the flow of current would again start. But if suppose if we consider a case something like the salt bridge pumps one of the ion much faster than the other. Suppose in the anodic chamber we had excess positive charge, this is pumping negative charge to the anodic chamber and neutralizing the solution, and in the cathodic, because it has excess negative charge, so it has to pump out some positive charge. Now suppose the positive charge that is pumped from the salt bridge into the cathodic chamber is very slow. So what would happen? The anodic chamber would get neutralized first, but cathodic won't get neutralized at that point of time. So again the flow of the current would get disturbed. So we'll say that the ions which are present inside the salt bridge should move at a equal rate, so that both the solutions are neutralized simultaneously. So for neutralizing it, so we need to have the cation and anion that are having the same mobility, that is at the same time they are going into the solution with the same rate, with the same speed and neutralizing them. So the electrolyte is chosen in such a manner so that their ionic mobilities are same. So you can read that the ions in the salt bridge should not react with the contents of either of the cathode or anode, and the ionic mobility of cation and anion of the electrolyte in the salt bridge should be same. So we'll choose the electrolyte which has cation and anion having the same ionic mobility. Okay, so salt bridge, the components of the salt bridge should not go into the solution and react with the solution. Okay, so that is the one thing, because if the reaction happens, so again there would be decrease in the concentration of ion, and again we will not be able to extract current from it. So the components that are present in the salt bridge should not react with the cations and anions in the solution. Second, we are saying that the ionic mobility of cation and anion of the electrolyte should be same. Okay, hope this is clear to you. Okay, hope this is clear to you. So I will quickly revisit, because this is the very basic, this is the very foundation. You need to understand. Once you are clear with this, questions are relatively easy to handle. So we are saying that this is your LHS, left hand side is your anode and right hand side is your cathode. Okay, so what we are doing, anode we have dipped zinc in the zinc sulfate solution, and in the cathode we have dipped copper in the copper sulfate solution. Now we know that the oxidation potential of zinc is 0.76 volt, and reduction potential of copper is 0.34 volt. So you can clearly make out that reduction potential of zinc was 0.76, whereas oxidation potential of zinc was 0.76 and the reduction potential of zinc 2 plus was minus 0.76. So the tendency of zinc to get oxidized is more than that of zinc 2 plus getting reduced. So what would happen over here? Zinc would keep on oxidizing. So some zinc from the rod would oxidize and enter into the solution as zinc 2 plus ion. Okay. Now the electrons which are liberated through oxidation would be on the rod. So due to which this rod acquires negative charge. So we are also saying that this is the negative terminal. So anode is the negative terminal in a galvanic cell. Okay. Now these electrons go and enter into the cathodic chamber. Now once this electron comes on the cathodic chamber, the copper 2 plus ion, okay, in the solution will gain these electrons. Okay. So copper 2 plus will gain these electron and it will take up 2 electron and change into copper. So this copper would get deposited at the, okay, so this copper would get deposited at the rod. Okay. So we'll say that this is the positive electrode or the cathode of the galvanic cell. Okay. So this was the basic skeleton. Now we know that there is excess positive charge created here and excess negative charge that is created over here. So neutralize them, we take a salt bridge. So this salt bridge has a porous end, okay, so that ions of the cathode or the anode does not enter into this and comes over here. Similarly, the cation or anion of the cathode does not enter and comes over here. So this will not allow the mixing of the two solutions, but it will keep on pumping ions so that the excess charges are neutralized. So when the excess charges are neutralized, again the electron flow would start. Okay. So this was the basic setup of the galvanic cell. This is also called as the Daniell cell. Okay. So this is the example of a Daniell cell. Okay. Hope this is clear to you. So whenever a system has been given to us, first we have to analyze it properly. We have to understand the very intricate details of it, and then we are going to approach all the questions. Okay. So if you look at the anode, if you look at the negative terminal, now I've already told you that anode is that electrode where oxidation takes place. So in anode we know that zinc solid is getting oxidized into zinc 2 plus aqueous and 2 electrons. Okay. Similarly at cathode, okay, I will say that copper 2 plus in the aqueous solution is taking up the 2 electron and getting reduced into copper solid. Okay. So for anode I will write the oxidation potential. Okay. So this is 0.76 volt. Okay. For cathode, because it is reducing, copper 2 plus is reducing. Okay, it is taking up the 2 electrons, so I will write its reduction potential. So this would be the value. Okay. Now if you add both the reactions, we will get the overall cell reaction. Okay, overall reaction that is happening in the cell. So when you are adding, we know that the 2 electrons would get cancelled out. Okay, so these electrons would get cancelled out. So we'll say that zinc solid plus copper 2 plus, okay, is changing into zinc 2 plus plus copper. Okay. So this is the reaction, overall reaction that is happening in this Daniell cell. Okay. Hope this is clear to you. So what you are going to do, whenever a cell is given to you, you have to write its oxidation half or the anodic reaction or the reduction half or the cathodic reaction. Once you have written the reaction, okay, for anode generally you follow this convention. Even you can write reduction potential also, but this is how I deal with it because things get simple for me in writing in this manner. Okay. So for anode, because oxidation is taking place, so data has been given to us of oxidation potential, so I will write oxidation potential over here. For the cathode, I will just write the reduction potential over here. Okay, because it cathode reduction takes place. Okay. Now if I want to calculate the overall EMF, okay, so I want to calculate the overall standard electrode, okay, overall EMF at standard conditions. Okay, so if I want to calculate the overall EMF at standard condition, so this will be equal to the oxidation potential of anode plus a reduction potential of cathode. Okay, so I am just simply adding them. Okay, anode oxidation, write oxidation potential, cathode reduction, write reduction potential. When you add them, you get the overall reaction. So the overall EMF will be, okay, oxidation potential of anode plus reduction potential of cathode. Okay, so this is again a very important point. Okay, so this is how you write the overall EMF. Okay, you can also write the overall EMF as, okay, we know that oxidation potential is always minus of reduction potential. So I can write this as E naught reduction potential of cathode, okay, and we know that this is minus reduction potential of anode. So I will just replace it by reduction potential of anode. Okay, so instead of oxidation potential of anode, I am writing a reduction potential of cathode. Okay, so the overall EMF of the cell is also a reduction potential of cathode minus reduction potential of anode. Now this you can easily understand because in this both the terms were different. One was according to oxidation, other was due to reduction. Now if you see in an overall cell, we say that the cathode chamber will always undergo reduction. Okay, so it will be always at a higher reduction potential as compared to the anode where oxidation is taking place. So the overall EMF will be, okay, reduction potential of cathode because it is higher, because it is at a higher reduction potential minus reduction potential of anode. Okay, so this is how you calculate the overall EMF. Okay, hope this is clear to you. You can have a look at this now. So what we are doing, we are writing the first anodic reaction, okay, the reaction that is happening in anode. Then we are writing the reaction that is happening in cathode. Then we are writing the overall reaction, okay, just by adding. Okay, so we know the value of the different oxidation and reduction potential. So we'll say that overall EMF of the cell at standard condition will be oxidation potential of anode plus reduction potential of cathode. Okay, this is easy to remember, that's why I use this formula more, but in standard text this is always the main formula. Okay, I remember it because oxidation we know will take place at anode, so it will have some oxidation potential. Reduction will happen at cathode, so it will have reduction potential. So when you are adding them, okay, we will get the overall reaction. So after that, if you add the oxidation reduction potential, you will get the overall EMF. But this is more logical formula to understand because one is at a higher reduction potential and the other is at a lower reduction potential. So just subtract that, you will get the EMF of the cell. Okay, so hope this is clear to you. Hope this formula is clear to you. So we are going to use this formula a lot. Okay, hope it is clear to everyone. Okay, so just let me so if you look at this Daniell cell, okay, so I will be saying that electrons are moving from anode to cathode. Okay, electrons are moving from anode to cathode in external circuit, and the flow of current is always opposite to the flow of electrons. Okay, so if electron is moving from anode to cathode, then the direction of current would be from cathode to anode. So in the external circuit, okay, so we'll say that in the external circuit, okay, in the external circuit, we'll say that the electron, okay, the movement of electron is from anode to cathode. Okay, anode oxidation, electrons are released, it will go to the cathode where reduction is happening. So the flow of electron is from anode to cathode. The flow of current in external circuit, okay, in external circuit is from cathode to anode because the movement of current or the flow of current is opposite to that of flow of electrons. Okay, so flow of current in the external circuit is from cathode to anode. Now if we talk about internal circuit, okay, so internal circuit there is no flow of electrons. Okay, as visible over here, the electrons are moving from anode to cathode. Okay, the voltmeter will show deflection indicating that the electron has started to move. But internal circuit, you can see that there is no flow of electron, it is just the flow of ions from the salt bridge into the solution that will constitute the flow of current. Okay, so in internal circuit we will say that flow of ions from salt bridge, okay, constitute the flow of okay, will constitute the flow of current. Okay, hope this is clear to you. So this is again a very standard question that is asked. Okay, if you look at in many textbooks or in many objective books, so there is a question on the flow of current. Okay, and we know that the overall EMF of the cell under standard condition is always reduction potential of cathode minus reduction potential of anode. Okay, I can also write a reduction potential as negative of oxidation potential. So if you write reduction potential as negative of oxidation potential, so this will become reduction potential of cathode plus oxidation potential of anode. Okay, now for a cell to be spontaneous, I am just going to cover this. For the time being, we are just going to accept the fact for a cell to be spontaneous, spontaneous means it, okay, the redox reaction is happening spontaneously and we can obtain electrical current from it. So for a cell to be spontaneous, its overall E naught cell should be positive. Okay, so when the overall E naught cell is positive, we will say that this cell is spontaneous. Okay, hope this is clear to you. Okay, so you can just have a snapshot of this for preparing your notes. Okay, so the overall EMF of the cell is always reduction potential of cathode minus reduction potential of anode. The current flows from anode to cathode. So the electron flows from anode to cathode. The flow of current would be from cathode to anode in the external circuit. In the internal circuit, the flow of current is maintained by the movement of ions from the salt bridge in the solution. Okay, so this is how you can find the EMF of a cell. Okay, so suppose we want to find the EMF of a Daniell cell. Okay, so now we know that in a Daniell cell at anode oxidation is taking place. So zinc would get oxidized into zinc 2 plus 2 electron. We know that reduction potential of this is minus 0.76 volt. Okay, and at cathode a reduction of copper 2 plus is taking place. Just we have done this. So this is changing into copper solid. Reduction potential of this is plus 0.34 volt. Okay, so if you want to write the overall reaction, okay, so overall reaction that is happening would be zinc plus copper 2 plus aqueous changing into zinc 2 plus aqueous plus copper solid. Okay, so the E naught cell of this reaction would be reduction potential of cathode minus reduction potential of anode. Okay, so reduction potential of cathode was 0.34 volts and reduction potential of anode was minus 0.76 volt. So this is 1.1 volt. So a Daniell cell generates a standard EMF of 1.1 volt. Okay, so this is how you calculate the standard EMF, overall EMF of the cell. Okay, so we know that the overall EMF has to be positive for the reaction to be spontaneous. Okay, hope this is clear to you. Okay, so this is a very basic that we wanted to understand. Now I am not starting with much of a problem solving now because I want to cover each and every detail of the concepts. Okay, so after studying the representation of overall cell, after studying the different type of electrodes that exist, then we'll combine all the concepts to solve numericals. Okay, so just maintain a good balance of theory. If you know all the theory, then the problem solving becomes very easy. The only problem is we just start solving questions, okay, much ahead before covering all the syllabus, okay, all the theoretical portions. So just have some, okay, good amount of reading. Just keep on reading so that you have all the basic understanding of the phenomena. Okay, so now let us look at the representation of overall cell. So if we want to represent the overall cell, I will not just keep on drawing this every time. Okay, it is a very tedious job. Neither questions will obviously have everything drawn over there. So there has to be some short notation to represent this cell. Okay, something like this was written over there. Okay, so I am just going to explain how do we write the cell representation. Okay, so there are some basic guidelines of writing a overall representation of a cell. Okay, the first thing is you can clearly see that anode will always be on the left side and the cathode will always be on the right side. Okay, so whenever you are drawing any cell, overall cell, okay, so we know that the anodic chamber would be at the left hand side, okay, and the cathodic chamber would always be at the right hand side. Okay, so anode is always on the left hand side, okay, that is on the right side, oh sorry, that is written first. Okay, so anode is always written first, so this is on the left hand side, and the cathode is always written on the right hand side. They are connected, okay, the electrodes are connected and they are connected with a salt bridge. So this is how a overall cell was made. Okay, so first point is very important, anode is always written first. So in the cell representation, the starting would be the anode. So left hand side is always anode and right hand side is always cathode. The second point is cathodic half cell and anodic half cell are separated by a salt bridge. Okay, you can see that anodic half and cathodic half, they are two separate half cells. This is called as one half cell, this is called as one half cell. We join them and we get the overall cell. So you can see that these two cells are separated by a salt bridge, okay, or they are connected by a salt bridge, we can say that. Okay, so whenever it is the case, so we'll represent it by a double bar. Okay, so we'll say that cathodic half and the anodic half are separated by a salt bridge. Okay, so they are separated by a salt bridge or connected by a salt bridge. So we'll say that we'll always write anode on the left hand side. Okay, I am writing anode on the left hand side and cathode on the right hand side. Okay, and they will be separated by a double bar. Okay, so this will indicate that this is the anodic portion, this is the cathodic portion, and they are connected by a salt bridge. Okay, hope this is clear to you. In each half cell, okay, the species are written in a manner to indicate the oxidation or reduction. Okay, so we'll write in anode, obviously the oxidation was taking place, and in cathode reduction was taking place. So we'll write the species in such a manner that we are able to understand that the species is undergoing oxidation and the species in cathode is undergoing a reduction. Okay, just like this case. Okay, just look at this one. Okay, so we'll say that this is your anodic half and this is your cathodic half. Okay, so we have written anode first followed by cathode and they are separated by a double headed arrow. So we'll write the species over here. So in the anode, if suppose we are dipped a metal in its aqueous solution, okay, so we'll write metal and then metal ion because metal is undergoing oxidation into metal ion. So in each half cell, these species are written in a manner to indicate the oxidation or reduction reaction. Suppose in the cathode we have some X ion, okay, and that was getting reduced into X. Okay, so you can see that M is getting oxidized, M changing into Mn plus, Xn plus getting reduced. So we are writing them in such a manner that we are able to understand that they are undergoing oxidation and reduction. Okay. Now, while writing the anodic and the cathodic components, if the phases or the states of the two material of the two species are different, then we have to separate them by a bar, by a single bar. Double bar means there is a salt bridge. Now we know that metal was dipped in a metal ion solution. Okay, so metal was in the solid phase and the metal ion was in the aqueous phase, so they has to be separated by a single bar. Okay, similarly in this case also in the cathode we know that Xn plus, okay, was in the aqueous form, whereas the X solid that was dipped in the solution, okay, was in a different state. Okay, so they will be again separated by a single bar. So that is again a very important point. So the species in different phase is separated by a single bar and their activity, concentration or pressure are written in brackets. Okay, so hope this is clear to you. So just remember these things, because if you are clear with this representation of an overall cell, because in question the cell will come something like this. So you have to understand what is happening in the cell, then only you will be able to proceed. Okay, so anode is always written first, that is on the left hand side, and cathode is written on the right hand side. They are separated by a double bar indicating that there is a salt bridge between them. Okay, in the anodic portion we will write the species in such a way that they represent oxidation, and in the cathode they represent reduction. So we will write it as, because in anode suppose we dipped a metal in its aqueous solution containing Mn plus ion, and in cathode suppose we dipped a X metal containing its ion in the aqueous form Xn plus. So metal will get oxidized in the anodic half, and in the cathodic half zinc Xn plus will get reduced. So we are writing them in their oxidation or reduction reaction form. Now if the phases are different, now we know that the metal is in solid state, the ions are in the aqueous phase, the ion are in aqueous phase, and this is in the solid phase. So they will be separated by a single bar. And if some concentrations are mentioned, so we will mention the concentration. Suppose the concentration of this was mentioned as C1, so we will write in square bracket, concentration of this was mentioned as C2, so we will write this in as C2. The last point is the electrode is mentioned at the start of anode and the end of cathode. If there is a electrode which is a non-reactive electrode, something like platinum, because this you will understand when we do different type of half cells. But if suppose a non-reactive electrode is also there, so we will also mention the electrode at the start. So we will mention the electrode at the start. Suppose platinum was the electrode, then we have to mention platinum. In this case there won't be any electrode because metal itself is acting as the electrode. But if in some case there is an electrode which is non-reactive, so you have to mention the electrode at the start of the anode and at the end of the cathode. So this is how you do the basic representation. So let me show you an example. Suppose this was our Daniell cell which we have already done now. Now we want to write the overall representation of this. So what we are going to do, now here we know that this is the anodic portion and this is the cathodic portion. So first we have to write the anode, and in the anode we will write species in such a way that they are representing the oxidation reaction. So we know that in the anode zinc is getting oxidized, so we will write zinc, this is in solid phase, and zinc 2 plus, this is in aqueous phase. Now whenever their phases are different, they will be separated by a single bar indicating that they are in different phases. So this is the basic thing in the anode. You can also write this as zinc sulfate, there is no issue, because sulfate ion is a non-participating ion in the reaction, so we are not writing it. You can write this as zinc sulfate, there is no issue. If some concentration is mentioned, so we will also write its concentration in brackets. Now this is the anode, after this comes as the cathode. So they are separated by a salt bridge, so 2 bars indicating the salt bridge. Now in the salt bridge we know that there is a reduction happening, copper 2 plus is taking up 2 electron and changing into copper, so copper 2 plus aqueous changing into copper, because their phases are different, so we will separate them by a single bar, or we will write the concentration as, suppose its concentration was C2, then we will write this as C2 in the brackets. So I can also write this as zinc solid, zinc sulfate aqueous whose concentration was C1, copper sulfate C2, and copper solid. So this is how you represent this cell. Hope this is clear to you. Now this is like when I was doing electrochemistry, I did a very less amount of problem solving, but I was more sticking to the theory and I was clear with all the cases, especially when I talk about different type of half cells, which I am going to do it tomorrow. So if you are clear with different type of 5 half cells and you know how you are representing it on a cell representation, then believe me, every question is just a very easy thing. It's just a basic calculation that you have to carry out. So understand the basic theory, put a lot of time in understanding the theory. If you are clear with it, then numerical solving is not difficult at all. So this is how you represent the overall EMF of this cell. Now one shortcut, like when I was in my school, so obviously at this stage you are not exposed to that amount of learning, so I did some tricks to understand how to write it. So what it might sound very silly to most of you, but this is how you do it and it is very easy to write. So what I assume that suppose I am standing over here, So I am standing over here and I want to come over here. Okay, suppose I want to come over here. Okay, so I am standing over here and I just want to come over here. Okay, I hope you got it. So I am standing over here, I want to come over here. So what I am going to do now, so I am just going, I cannot come from here. So what I am going to do, I am just going to jump inside this. Okay, now I don't know the depth of this. So what I am going to do, there is a rod over here. So somehow I am going to hold this rod. Okay, if I hold this rod, okay, I am going to hold this rod. Okay, I am just going to hold this and somehow I am just going to go down. Okay, so I just catch hold of the anode. So first I encountered was anode, then through the anode I entered into the solution. Okay, so I entered into the solution. So solution zinc 2 plus ion, solution zinc sulfate or zinc 2 plus ion. So they are in different phases, so separated by a bar. Now once I have entered over here, okay, so what I want to do, I want to enter into this salt bridge. I will enter into this tunnel and through this I will come over here. Okay, so I will enter into this tunnel and through this I will come into the solution first. So I am going to get the copper 2 plus. So after that I am going to get copper 2 plus and from here I am going to again get hold, just somehow like hold the electrode, copper electrode and just going to climb. Okay, and I am going to reach. Okay, so this is how you can also do. So you have to start from anode. Okay, just enter into the anode through the electrode. So you will first encounter the rod followed by the ions in the solution, then through the tunnel or the salt bridge you are going to land up in the cathode. So you are going to enter into the solution first, so that will have ion first and then you are somehow going to cling to the rod and come out. Okay, so this is how you represent it. Okay, this will work in almost every cases. So that's why I just like out of my curiosity and out of my imaginative power, I just devised something very silly so that I could understand the working of a cell or the overall representation. Because at that time when like new questions were coming, so we were not able to understand what is happening there in the cell representation. Okay, so this is how you write the cell representation. Okay, so just let me ask you one thing. Suppose we are having, okay, I want to design a cell. Okay, now this is how scientists do it. Okay, we want to design a cell. We know some basic reduction and oxidation potential. Suppose I knew the reduction potential of silver plus changing into silver. Okay, so this is reduction potential of silver ion. Okay, this is 0.8 volt. Okay, I want to say I have copper 2 plus reduction potential is 0.34 volt. Okay, so now the question comes, can I design a cell which produces current using these two datas? Okay, so obviously I can see that the reduction potential of silver ion is more than that of copper 2 plus ion. So if I am combining them together, so obviously silver ion has the more tendency to get reduced. So silver ion will be overall undergoing reduction and then the copper has to undergo oxidation. Then only redox reaction would happen and then only we will get current. So what I will say, I have to take this as cathode. So in cathode what I will say, okay, Ag plus is taking up an electron and changing into Ag. Okay, so this is solid, this is aqueous. So the reduction potential of this is 0.8 volt. Okay, similarly at anode, copper 2 plus would be taking up 2 electron, okay, and changing into copper solid. This is aqueous. Okay, so the reduction potential of this is 0.34 volt. Okay, so because we have to write the oxidation reaction. Okay, so this is basically the reduction reaction. So I am just going to write the oxidation reaction of copper. So copper solid is oxidizing into copper 2 plus, aqueous plus 2 electron. So the reduction potential of copper 2 plus was 0.34 volt. I could have also written this as oxidation potential of copper, that would be minus 0.34. Okay, so now when I am adding this, okay, hope this is clear to you. I have to design a cell, I have been given these two data, so I have to design a cell which spontaneously produces current. So I can see that the data has been given to us in which the reduction potential of silver ion is much more than that of copper 2 plus ion. That means in the overall cell, silver ion has to undergo reduction. So this will have to act as a cathode and this has to act as an anode. So if it is acting as a cathode, we know that at cathode reduction would take place. If this has to act as an anode, so we know that oxidation would take place. Now we'll write the reduction potential of this, which is 0.8. We can write the oxidation potential, okay, but I am going to write reduction potential only. So reduction potential of copper 2 plus ion was 0.34 volt. Okay, so when you add this, now we cannot directly add it because there is only one electron, there is two electron over here. So we have to multiply this with 2. Okay, so when you multiply this with 2, this will become 2 Ag plus aqueous. This will become 2 electron. These will get cancelled out, plus copper solid. Okay, will change into 2 Ag solid plus copper 2 plus aqueous. Okay, hope this is clear to you. Now next question that comes in, now this is very logical. If you multiply the reaction with say any factor n, will its standard electrode potential change? Standard electrode potential won't change, okay, because it is a fixed value. So even if you multiply with any number, its value would remain same. Okay, so the overall E naught cell for this reaction would become reduction potential of cathode. Okay, so I am writing this as reduction potential of anode minus a reduction potential of anode. Okay, so reduction potential of cathode we know is 0.8 and reduction potential of anode we know is 0.34. So this would come out to be 0.46 volt. Now you can see that E naught cell is positive. Okay, so this is a spontaneous cell. The reaction, redox reaction is spontaneous. So this will allow us to draw some current from the cell. Okay, so this is a working cell now. Okay, hope this is clear to you. You could have also written like the one which I have already told you. Instead of reduction potential, you can write oxidation potential as well. Now this oxidation potential would be that of copper, okay, because reduction potential of copper 2 plus was given. So oxidation potential would be of copper. Okay, so overall E naught cell you can also write as a reduction potential of cathode plus oxidation potential of anode. Okay, so if you do this, you will get the same value only. Okay, so hope this is clear to you. So what we have to do over here, we have to take a anode, we have to take a cathode. Okay, so this is called as the oxidation half cell. Okay, sorry, reduction half cell or the cathodic half cell. This is called as the anodic half cell or the oxidation half cell. So we know that anode has to be on the left hand side and cathode has to be on the right hand side. Okay, so in this we know that we are having, okay, anode we know that it is now copper dipped in copper sulfate solution. Similarly in cathode we know that it is silver rod dipped in aqueous silver nitrate solution or the solution containing the silver ion. Now we can connect them through a external wire, conducting wire, and to complete the internal circuit we have to add a salt bridge. Okay, so if I want to write the overall EMF of this cell, overall representation of this cell, I will write, okay, anode has to be written first. So in anode what I will write first? Copper, because that is the species that is getting oxidized, changing into copper 2 plus. You can write this as copper sulfate, but because sulfate is a non-participating ion in this entire reaction, so you can neglect sulfate in the expression. Okay, so copper solid changing into copper 2 plus, suppose its concentration was given as C1. So we'll write its concentration. Okay, then this is over, so there is a salt bridge represented by double-headed arrow. Then here we know that in the solution we are having Ag plus or the AgNO3 aqueous, say concentration was C2 followed by silver salt. Okay, so these are the electrodes. We write the electrode at the start and at the end. Okay, start of the anode, end of the cathode. Okay, if it is a non-participating or an inert electrode, then also we have to write it. Okay, so that I will show when I show the standard hydrogen electrode cell. Okay, so this is how you represent the overall EMF. Okay, so shortcut again, if you are standing over here, you want to come over here. So what I will do, I will just cling on to this rod. So I will just get hold of the copper first. So copper I am writing first, copper solid. Then I will enter into the solution. So this will be copper 2 plus aqueous. Then through the tunnel, I am moving into the salt bridge into the cathodic half. So I got that tunnel as a salt bridge double-headed arrow. Then when I enter into the solution, I will first encounter the ions. So I have written Ag plus. Then I will just get hold of this rod and come outside. So that is again a silver. Okay. So hope this is clear to you now. Okay. So overall EMF is also clear to you. Okay. So this is the very basic that you should know. Okay. So let us just have a look at some of the questions. Okay. So this is the first question. So this says that the cell reaction 2Ag plus hydrogen changing into 2H plus 2Ag solid is best represented by. So we have to just write the cell notation of the given reaction. So from the reaction you can see that, okay, at cathode there would be a reduction of silver ion, okay, because in the reaction itself is given to you that Ag plus is changing into Ag. At anode we know that oxidation takes place, okay, you can see that hydrogen was there, it is changing into H plus. So hydrogen gas is getting oxidized into H plus ion. Okay, so if we want to write the overall reaction, we have to just multiply this with 2. Okay, we know the reduction potential of silver ion changing into silver is 0.8 volt. We have just written it now. Okay, for the hydrogen and H plus, the reduction potential is always 0. I am going to discuss this in detail, so don't worry about this. So for the time being, just accept this data. I have also shown you the entire electrochemical series data. I have shown that H2 changing into H plus or H plus changing into H2 will always have a electrode potential of 0. Okay, so when you multiply this with 2 and add, so we will have 2Ag plus, okay, plus hydrogen gas, okay. Now these two electrons will get cancelled out, 2 silver plus 2H plus. So if I want to write the overall EMF of this cell, so this would be reduction potential of cathode minus reduction potential of anode. Now reduction potential of cathode is 0.8 and reduction potential of the anode is 0. So this would be 0.8 volt. So again this is a spontaneous cell. Now if we want to write the cell representation, so now we know that anode is hydrogen and H plus. Okay, so in anode the species are hydrogen and H plus, and in cathode it is silver and silver ion. So what we are doing in cathode, we are having a silver rod, we are dipping it in silver ion solution. Okay, so this is silver ion or silver nitrate. So silver is dipped in silver ion. So this is your cathodic end. Now for the anodic end, we know that in solution it has to be H plus. Okay, so solution is basically say dilute HCl. Okay, so this has H plus in it. Now, like where is the cathode? Okay, oh sorry, where is the anode? So we cannot directly bubble hydrogen into the anode. So what we are going to do, we are going to have an inert electrode over here. So it is something like this. Okay, so we are having a platinum wire. Okay, so this is the platinum wire. Okay, so this is your platinum wire, and through this we are sending hydrogen gas inside the solution. So hydrogen gas gets absorbed on the platinum and then it can enter into the solution, and then we are connecting them through a conducting wire. Hope this is clear to everyone. Okay, now we have to connect a salt bridge to complete the circuit. Okay, so this is the setup for hydrogen H plus. Because hydrogen cannot be directly pumped into the solution, so we are taking a help of a non-reactive, okay, electrode, that is platinum. So we are passing hydrogen gas on this platinum wire. So this is getting absorbed and it is going into the solution. Okay, so this is the main cell. So if I want to write the representation, so first I have to write anode. So what I have already told you, when I want to have anode, so I will just enter into this tube. Okay, so when I enter into the tube, I will first encounter platinum. Okay, so that is how I am going to go inside. So I have to get hold of the platinum first. So that is platinum solid. Okay, now when I am going inside, there is a hydrogen that is always coming from outside, so I am going to have hydrogen gas. Okay, and when I enter into the solution, I will get H plus ion because all of them are in different phase, so they will be separated by a bar. Okay, now I will enter into the Sol bridge and will go towards the cathode, so I have a double bar indicating that Sol bridge is there. So when I enter into the solution, I will get silver ion, and then from that I will catch the electrode, that is silver, because they are in different phase, so they will be separated by a bar. So this is how I write this cell. Okay, so you can see this, the answer will be this. You can also say that because in the anode there is oxidation taking place, so H2 is changing into H plus, so H2H plus. Okay, they will be separated by a bar because phases are different. Ag plus and Ag at cathode separated by a bar. Okay, double bar indicating that there is a salt bridge between them. Okay, platinum is there because hydrogen has to go into the solution. Okay, so that is being done through a platinum wire. Okay, so platinum wire is dipped on which hydrogen is always sent, so that the hydrogen gets absorbed on it and enter into the solution. Okay, so hope this is clear to you. So this is how you represent. Okay, so if you look like in my lectures, I always start with the basic, I stick to the basic, I remain in the basic, and when I have done everything, I will just raise the bar. Okay, we will enter into the higher level problem solving when I am sure that I have incorporated all the theory in your head. Now you know all the basic theory from where I can take you to the highest level. Okay, so entering into the highest level is not recommended at all because that won't help you in building the basic blocks that is required to complete the chemistry. Okay, so just let us look at another question. So look at this reaction. Okay, so this says that there is a chromate ion reacting with H plus, iron 2 plus, changing into iron 3 plus, chromium 3 plus and 7 water. So what I am going to do first, I am going to write cathodic half and anodic half. Okay, so I can see that iron 2 plus is changing into iron 3 plus. It means that there is a oxidation happening. So iron 2 plus is getting oxidized into iron 3 plus. Okay, so this is the reaction that is taking place at anode. So if reduction potential is given of iron 3 plus, okay, because generally the data of reduction potential is given to us, so reduction potential would be given of 3 plus. Okay, we will get to know the oxidation potential of iron 2 plus. Now in the cathode we know that, okay, in the cathode we know that dichromate ion is there. Okay, this is getting reduced to Cr3 plus. Okay, so 2 Cr3 plus we know that there would be 7 water over here. Okay, plus 6 electron plus 14 H plus. Okay, so this reaction is there. Now we want to add the two reaction to get the overall, okay, reaction. So I have to multiply this with 6 so that the electrons get cancelled out. When you add, this electron is in the product, this electron is in the reactant, so they will get cancelled out. So we will get 6 iron 2 plus plus 14 H plus Cr2O7 2 negative changing into 6 iron 3 plus 2 Cr3 plus 7 water. Okay, so if you know the reduction potential of iron 3 plus, say reduction potential of iron 3 plus changing into iron 2 plus was say X volt, and say reduction potential of dichromate ion H plus was say Y volt. So the overall EMF of this cell under standard condition would be reduction potential of the cathode, because cathode is always at the higher reduction potential, that is Y, minus reduction potential of the anode. So reduction is taking place of iron 3 plus, so reduction potential of iron 3 plus, that would be X. So you have to see which data has been given to you, because question becomes tricky over here. Okay, suppose reduction potential of iron 3 plus not given over here, then we have to calculate it. So you have to look at the data, okay, that the data is complete and you can use it in the question. So just don't do it blindly, just have the observation. Okay, this helps you in developing a very good habit. So now if you want to construct the cell, so I know that I will have a anode, okay, and I have a cathode. Okay, now in anode I am having iron 2 plus and iron 3 plus. Now both of them are in aqueous phase. Okay, so both of them, iron 2 plus aqueous and iron 3 plus aqueous, okay, they will be in the solution. Okay, similarly if you look at the cathode, so in cathode we are having chromate ion H plus and we are getting Cr3 plus and water. So everything is there in the solution itself. So this will have dichromate ion. Okay, hope this is clear to you. So this is having dichromate ion H plus chromium 3. So everything is in the solution only. So now we have to connect them somehow. So because everything is in the everything is in the ionic form and they are present in the solution, so we'll have a platinum electrode dipped in them, because platinum electrode is a non-reactive electrode, so it won't cause any extra reaction to happen. So this will be basically used to pump the current, pump the electron from cathode to anode. So this is basically your anodic, that is negative, cathodic, that is positive, and we have connected them through a conducting wire. Okay, and we'll use a salt bridge. Hope this is clear to you. Okay, so you can understand where we are using the inert electrode. Okay, when metal is dipped directly in its metal solution, so we don't need any electrode because that metal itself will act as the electrode. But we are having species that are there in the solution and there is no species in solid state. So we need a non-reactive platinum electrode, or whenever we are a gas and a ion of it. Okay, so we need a platinum electrode. So if we want to write the cell notation, so obviously what I have told, I have to go inside the anode, come in the cathode and then come outside. So when I enter into the anode, I will enter through the wire. So first I will encounter platinum solid. Okay, so this is another phase solution. Then I will enter into the solution because they are in different phase, so they are separated by a single bar. Then in the solution we get iron 2 plus aqueous, comma iron 3 plus aqueous. If their concentration was given as C1, C2, we'll write them also, but in this case no concentration has been mentioned. Then we enter into the salt bridge. So this is a salt bridge where we enter this solution, we get the ions. So in that first we will write dichromate ion because it is undergoing reduction, H plus changing into Cr3 plus aqueous. Okay, suppose the concentration of this was given as C3, this was given as C4, this was given as C5. Okay, so after that what I will do, I will just catch the electrode and come outside. So after that we get the electrode, that is platinum, in a different phase. So I will separate it by a single bar. Okay, so this is the cell representation. So you can see that the cell representation over here is the best one is this one, because H plus is missing over here still. This is the best answer. Okay, so I hope you have understood this. Okay, I am taking little more time, like just discussing the basic over and over again, but believe me, in the coming lectures I will just increase the level of the lectures and you will get to see some of the classical and very important questions. Okay, similarly we can just write for this without designing the cell. So we know that in this chlorine is changing into chloride ion. Okay, so in anode we know that chlorine gas is changing into 2Cl negative aqueous plus 2 electron. So chloride will be in the solution, we have to pass the chlorine gas. So chlorine gas we cannot directly pass it, so we will dip a platinum electrode, through that we will pump chlorine inside the solution. Okay, so in the anodic chamber we will have platinum first, then chlorine gas, then Cl negative ion. Okay, then after that we will get the salt bridge. So in the cathode we know that silver ion will take up the electron and change into silver solid. Okay, so we'll get silver plus aqueous and then we'll get silver solid. Okay, so this is the representation. Okay, so if you have this representation, so overall reaction would be, you have to just multiply this with 2. So we'll get chlorine plus 2Ag plus changing into 2Cl negative plus 2Ag. Okay, so this is the reaction. Okay, so hope this is clear to you. So chlorine plus 2Ag plus changing into 2Cl negative plus 2Ag is the answer. Okay, hope this is clear to you. Okay, so just let me come into a very important portion of this chapter, that is Gibbs free energy. So we know that Gibbs free energy is generally used to determine the spontaneity of any process. If we know that delta G is negative, then we say that the process is spontaneous. If delta G is 0, we say that the condition is reversible or we are at equilibrium. If delta G is positive, then we say that the process is non-spontaneous. Okay. So Gibbs free energy is also, like when we were doing thermodynamics, you might have defined that there are two types of work, mechanical and non-mechanical. Okay. So non-mechanical work is basically observed by Gibbs free energy. So Gibbs free energy will basically determine the electrical energy or the non-mechanical energy. So the change in Gibbs free energy is also a measure of the maximum amount of work that can be performed during a chemical process. So this you might have done in thermodynamics also. So if you don't remember it, you can just have the conclusion, okay, that Gibbs free energy is also the measure of the maximum amount of work that can be performed during a chemical process. Okay. So we'll say that the electrical work, if we talk about the electrical work, so we know that the electrical work is also the charge into the potential. Okay. So just I am going to talk a basic thing. So we know that the charge on one electron is 1.6 into 10 raised to the minus 19, okay, coulomb. So if we talk about 1 mole electron, so 1 mole electron is basically this number. So the charge on 1 mole of electron would become this, okay, when you calculate this, so this will come out to be 96500 coulomb. So 96500 coulomb is also known as 1 Faraday. So 1 Faraday is basically charge on 1 mole of electron. Okay, so 1 electron we know that the charge is 1.6 into 10 raised to minus 19 coulomb. 1 Faraday is the charge on 1 mole of electron. So that is equal to 96500 coulomb. Now if you look at any galvanic cell, okay, so what we are saying that there is always some amount of electrons that is transferred from cathode to anode. Okay, so I have already shown you in these reactions. Okay, you can see that in this reaction overall it was 2 electrons from anode going into the cathode. So when you are writing the overall reaction, so the total number of electrons you are cancelling out, that total number of electrons is the number of electrons transferred between the two cathode and anode. Similarly, if you look for this case, okay, so if you look in this case, okay, so if you look in this case, we have already written the equation. You can see that we have multiplied this iron with 6. So total 6 electrons, moles of electron was getting produced from anode entering into the cathode, and that 6 electron was reducing to dichromate ion into Cr3+. So the number of moles of electron transferred from cathode to anode is 6. Okay. So to get the electrical work, we will say that, okay, maximum electrical, we will say that maximum number of electrons that is transferred, okay, so that would be N into, okay, 1 mole of electron is always having, is called as 1 Faraday. Okay, so suppose in a reaction 1 electron was getting transferred. Okay, so N would become 1. So we'll say that 1 Faraday of charge has been transferred. So suppose in a reaction, suppose we are talking about a Daniell cell. So now in a Daniell cell we know that zinc is getting oxidized and copper is getting reduced. So in anode 2 electrons are liberated, that is taken up by the cathode. So the number of electron transferred from cathode to anode is 2. So number of moles of electron transfer is again 2. So that is 2 Faraday. Okay, so N will become 2. Okay, so N into F is the total number of electron that is transferred from cathode into anode. Okay, into the E naught of the cell. Okay, that is the potential. So this is the maximum electrical work that we will obtain. Okay, so this is the maximum work that will obtain. Okay, so if we talk about delta G naught, that is Gibbs free energy under standard condition, so this is always minus maximum work, okay, that is N into F into E naught cell. Okay, so this is the value of delta G naught. Okay, so this you have to know that delta G naught is always minus N into F into E naught cell, where N is the number of electron transferred, overall number of electron transferred from anode to cathode. So when you are balancing the reaction, okay, when we are adding anodic half and cathodic half, so we are always multiplying with a certain number so that total number of electron get cancelled out. So when you multiply it with a particular number, so the number of electron in both the cases becomes same, and that total number of electrons is the total number of electrons transferred between cathode and anode. Okay, suppose in anode there was only 1 electron involved and in cathode there was 2 electron involved. So we are multiplying 2 with anode so that the number of electron became same. Okay, so total number of electron transferred between them is 2. So in that case N would become 2. Okay, hope this is clear to you. Let us take another case. Suppose in the oxidation half 2 electrons were getting liberated and in the reduction reaction 3 electrons were taken up. So to balance this reaction we will multiply the oxidation reaction with 3 and reduction reaction with 2, so that the total number of electron becomes 6 in both the cases, and when you will add, the electron will get cancelled out. So in that case from anode to cathode we know that 6 electrons are getting transferred, so value of N would become 6. F is your Faraday, 1 Faraday is the charge on 1 mole of an electron, okay, so that is equal to 96500 coulomb. E naught cell is the overall EMF of the cell. So delta G naught is always minus N into F into E naught cell. So delta G naught basically measures the maximum electrical work during a electrochemical process. Okay. So we know that if a reaction has to be spontaneous, so its delta G naught has to be negative. Now delta G naught will be negative because these are all positive quantity. E naught cell has to be positive because there is already a negative sign outside. So delta G naught will be negative only when E naught cell is positive. So we will say that a spontaneous redox reaction characterized by a negative value of delta G naught which corresponds to a positive value of E naught cell. So whenever you are doing any reaction, constructing any cell, so its E naught cell has to be positive, then only we will say that that cell or that process is spontaneous. Okay, hope this is clear to you. So in this I just wanted to discuss Nernst equation today. So I hope you knew this formula, that is delta G is equal to delta G naught plus RT ln Q. Okay, so Q was basically your reaction quotient, okay, that is similar to that of equilibrium constant. The expression is similar to that of equilibrium constant, only difference is, okay, equilibrium constants are measured at equilibrium, reaction quotient are measured at any time t which is not equilibrium. Okay, so I will just explain you through the expression. So let me just make you understand this. So I know that delta G naught now is minus N into F into E naught cell. Okay, delta G naught is Gibbs free energy under standard condition. Delta G is your Gibbs free energy under any other condition that is not standard. Okay, so delta G naught is always having a fixed value. Okay, but delta G can change. Delta G naught is basically when we are taking all the reactants and products in the standard state and their conditions are also standard one. So standard is basically temperature 298 Kelvin and pressure 1 atm. If we don't take that condition, if we take any other condition, temperature is not 298, the reactants and products are not in their they are not in their standard state, okay, the concentrations are not 1 molar, so then we have to express delta G. Okay, so delta G would become minus NF into E cell. Okay, so E cell is your EMF of the cell, okay, at any condition that is not standard. E naught cell is the standard EMF of the cell. Okay, so for calculating the standard EMF of the cell, we say that the concentration of all these species is 1 molar and the pressure of all the gases are 1 atm and the temperature is 298 Kelvin and the pressure is 1 atm. But if any of the condition is different, then we will not say it as a E naught cell, we will call it as E cell. Okay, so delta G naught is minus NF into E naught cell, delta G will be minus NF into E cell. So delta G naught is at standard condition, delta G is at any condition, plus RT ln Q. Okay, so if I just write this, I will write E cell as E naught cell. Okay, I am just dividing it by minus NF, so this will become minus RT by NF ln Q. Okay, so I can write E cell as E naught cell. I will change this. Okay, so this will become 2.303 RT upon NF into log Q. Okay, now we know that the value of, at standard condition, the value is 298, okay, Kelvin, Faraday is 96500, value of R is 8.314. So all of them are constant. So when you plug their values, so you will get this as minus 0.0591, or in many books it is also given 2. Okay, so R is 8.314, T is 298 Kelvin, F is 96500 Coulomb. You just plug these value, you will get this as the value. Okay, so this is log of Q. So this is your basic Nernst equation. Okay, so this equation is called as Nernst equation, that correlates the EMF of the cell with the concentration of all the species in it. Okay, so let me just take one example and make you understand this before we end this session for today. Okay, so let us consider the same reaction. Okay, so at anode of the Daniel cell, so at anode zinc solid was getting oxidized into zinc 2 plus aqueous plus 2 electron. Okay, at cathode copper 2 plus was reducing, so this was taking up 2 electron and changing into copper. Okay, so the overall reaction of this was zinc solid plus copper 2 plus aqueous changing into zinc 2 plus aqueous plus copper solid. Okay, so we knew the value of E naught cell. Okay, E naught cell would be a reduction potential of zinc 2 plus, okay, minus reduction potential of copper 2 plus, sorry, what I am writing. So this is basically reduction potential of cathode minus reduction potential of anode. Okay, so reduction potential of cathode would be reduction potential of copper 2 plus changing into copper minus reduction potential of zinc 2 plus changing into zinc. So E naught cell would become, we knew the value 0.34 and this is minus 0.76. So E naught cell was 1.1. You have to understand the difference between E naught cell and E cell. So E naught cell is basically the overall EMF of the cell when we are taking the standard conditions, that is temperature is 298 Kelvin, pressure is 1 atm, okay, and the reactant and product are in their standard state. Okay, the concentration of all the species is 1 molar. Okay, and the, if any gases are there, its pressure is 1 atm. But if you change any of the condition, if the concentration of the ions are changed, so we will not write it as E naught, we will write it as E cell. So the relationship between E cell and E naught cell is given by Nernst equation. So E cell would become E naught cell, okay, this is the relationship Nernst equation, minus 0.0591 upon n. You can see that number of electrons, n is always number of electrons exchanged between cathode and anode. Okay, so if you can see in this, number of electrons in the anode was 2 and number of electrons in the cathode was 2, so that was getting exchanged. Okay, so in this case there is no multiplying factor, so the value of n is 2, okay, into log of reaction quotient Q. Okay, so reaction quotient Q is basically, okay, this will be the concentration of zinc 2 plus, okay, raised to power 1, stoichiometry is 1, into solids we don't take in the expression, okay, divided by concentration of copper 2 plus raised to power 1 because its stoichiometry is 1. So this is the Nernst equation, EMF of the cell, okay, in terms of E naught and the concentration of different ion. So if you are just having any confusion, so if you are writing say 2A plus B changing into C plus 3D, if you want to write the reaction quotient, okay, so this will be equal to concentration of, this is basically the product of, okay, product of concentrations, okay, raised to the power its stoichiometry divided by product of concentration of reactants raised to the power its stoichiometry. So Q will be, okay, this is always product upon reactant, concentration of C raised to power 1, stoichiometry is 1, into concentration of D raised to power stoichiometry, that is 3, divided by concentration of A raised to power 2 into concentration of B raised to power 1. So this is basically your Q. Okay, so you can write the Q for any reaction which is given to you. So Q is basically the product of concentration of the product raised to power its stoichiometry. So we are just taking the concentration, okay, product of concentration of the product raised to power stoichiometry. So the product is C, so C raised to power D into D, its stoichiometry is 3, divided by okay, concentration of reactant, product of concentration of reactants, A raised power 2 into B raised power 1, okay. So this is how you get the reaction coefficient, reaction quotient. So this is measured at any time t, okay. So this is measured at any time t, okay. So this is your overall EMF. Now if in the question, suppose if you were given that the concentration of zinc is 0.1, okay, and the concentration of copper 2 is 10 raised to the minus 2. So you can just put this value over here, you will get the value of E cell, okay. So this is it for today. I wanted to discuss more, I wanted to have a discussion on, okay, we wanted to solve some question on this. You can take a snapshot of this, you can try this at your home, okay, just take a snapshot, I will give you the way, okay. Similarly, you can take the snapshot of this and try this question. I wanted to discuss about equilibrium constant and makes you do some problem solving, okay, but still no issue. We'll cover it in the next class, don't worry about it. We have ample amount of time left with us. So just, if you'll see the style of like my teaching, it is basically more of going into the theory first, cracking the full theory with lot of confidence, analyzing each and every basic cases that are there. Once I am sure of about everything, then my work as a teacher, as a mentor of improving you becomes very easy. Then after that I will raise the bar, I will keep on increasing the level of the question, we will go up to the Olympiad level questions as well. That is how we, like I have trained 2 AIR1 in JEE Advanced 17 and 18. So this is how people actually learn and they improve on a daily basis, and after some time they become master of the subject. Okay, so I hope you enjoyed the today's session. So I hope you are reading theoretical book as well. NCERT is recommended for reading now, okay. So tomorrow lectures will be very interesting because we are going to talk about different type of half cells and we are going to connect all the basic theories, okay, and the next, after that, next 2 class will be pure solving on galvanic cell, because galvanic cell is a very important topic, sure topic for JEE Advanced as well as chemistry Olympiads, okay. So if you are preparing for the Olympiads as well, so this is a very important chapter, okay. So I hope everything is fine at your side. So this is it for today. So this is Animesh signing off for now. We'll catch tomorrow for some very interesting sessions on electrochemistry and lot of problem solving. So stay happy and stay blessed. Thank you.